Hey folks, in lesson 19 we're going to have one more application of energy. And this is going to be using energy, our expressions of energy, kinetic energy and potential energy, to derive an equation of motion for simple systems in which energy is conserved. Now, everything that we've done so far in Chapter 5, dealing with energy, you've likely seen before in your physics course, in which we're solving for energy at one point, solving for energy at another point, and then from that determining how the system state changes between those two particular points. This is going to be a departure because now we're actually pulling in more of what we've learned from earlier chapters. We're getting the same result of what we learned in earlier chapters, such as deriving equations of motion using F equals ma. So the best way to do this is to just go through a couple of examples. So the first one that we have is the simple pendulum, which we've seen before. We all know the equation of motion for this. So let's use energy to get that. First, we put on our inertial reference frame, in which we have E1 along OP when theta is equal to 0, E3 coming out of the plane of motion, and then E2 being the cross product of E3 and E1. And then we apply a polar frame, B, which has an origin at the same point O. We have a vector ER that's in the direction of OP that moves along with the pendulum, and EZ, which is along the line of E3 out of the plane, and then an E theta, which is the cross product of EZ and ER. Now, to apply this method, we need to determine whether energy is conserved, because we can only do this if energy is conserved in this system. And so we know well from the last lesson that energy is only conserved when the work due to non-conservative forces, R, P with respect to O, along the path, along any path actually, is equal to 0. And so we can calculate what this work is, and if it's equal to 0, we can apply this method. So to do that, we need to first identify what our non-conservative forces are. So we'll draw a free body diagram, and on our free body diagram, we're going to have two forces. So gravity is acting on this pendulum, so we have the force due to gravity, and this is in the E1 direction. And then the only other force that we have acting on the system is going to be the constraint force, which is the tension that's in the pendulum arm. We'll put that in the negative ER direction. And in looking at these forces, we know that gravity is a conservative force. And then this constraint force, T, would be non-conservative. So that means we need to calculate the work done by the constraint force T and see if that's equal to 0. So the work on the particle done by the force T, P with respect to O, along the path, is equal to the integral of the force, which is negative T in the ER direction, dotted with the velocity, L theta dot, in the E theta direction, dt. So this is our definite form of this integral. So we're integrating across T1, some T1 to TF, and then this is where the force here is the non-conservative force, and then where this is the velocity of P with respect to O observed in the inertial reference frame. And this velocity comes from our kinematics, which we've done on this pendulum multiple times, where we have our position vector r, P with respect to O, is equal to the length L in the ER direction, and then the velocity of P with respect to O in the inertial reference frame is L times theta dot in the E theta direction. And that's simply using our kinematics of our polar frame that we can derive using our position vector. But the important part here is that we have in our expression for our definite integral is, no matter what, as we're adding up the area under this curve over time, this is always equal to 0 because it's ER dotted with E theta, these basis vectors are orthogonal with each other, so when we take the dot product of them, it's equal to 0, and regardless of how many times we add that, the work due to this non-conservative force is always going to be 0. So this tells us that energy is conserved in this system. And so we can calculate our equations of motion using this system or using this method. And so here's what this looks like. If energy is conserved, then that means that the time derivative, as observed in the inertial reference frame, of our energy, this is P with respect to O, is going to be equal to 0. So we find an expression for our energy that's a function of the state. So essentially saying it's a very generic expression. It's not at a particular time, like a time 1 and then a time 2, like we've done before, but instead it's a function of the state, and then we'll get this analytic expression. We set this equal to 0, and then, as you know, an equation of motion is always a scalar equation. It's a second order differential equation. So we'll just solve for the second order differential variable, and that should give us our equation of motion, which we know in this system is theta double dot is equal to negative g over L sine theta. So let's determine an expression as a function of the state for the total energy of the system. And so that's going to be the kinetic energy of the system plus the potential energy of the system. So for our kinetic energy of the system, T of P with respect to O, this is equal to 1/2 m multiplied times the velocity, the norm of the velocity of P with respect to O, as observed in the inertial reference frame, squared. We plug in our values here, so it's 1/2 m. We know that our velocity is L theta dot, and so we'll put that in there as the norm, and then square that, and then we get from this 1/2 m L squared theta dot squared. So the next is our potential energy, P with respect to O. And this potential energy is going to be the potential energy of all of our conservative forces. And so our only conservative force in this system is the force due to gravity. And so we know that our potential energy due to gravity, the expression in the book is mgy. And so it's important to note here that this y is the displacement above point O. So the displacement above point O. And the reason why this is point O is because we're taking everything in this system, this is in our equation here, we're saying our energy using O as our reference point, our kinetic energy and our potential energy using O as our reference point, O being an inertially fixed point. And so this needs to be the displacement above point O because the force due to gravity is pointing down. So that means we need the displacement in the negative E1 direction. So our expression here for mgy is going to be mg, these are simply two scalars, and then to get that displacement above point O, we need to take our position vector, r, p with respect to O, and then we're going to dot this with the negative E1 direction. And so by dotting a position vector with a unit vector in a particular direction, that gives us the scalar value in that direction. So this will give us the scalar value above point O in the direction above, the scalar value above point O in the right direction. So let's fill this in. This would be mg, and then our position vector is L in the ER direction. This is dotted with the negative E1 direction, which means we have negative mgl, and then multiplied times ER dotted with E1, and then ER dotted with E1, we have our ER and our E1 using our transformation table is cosine theta, so we get the answer here of our potential energy due to our state is negative mg L cosine theta. All right, so let's just make sure that makes sense. Negative mgl cosine theta. Let's go back here. And we should see that what we're looking for is really this distance below, which means it's a negative direction. So our potential energy is going to be negative potential energy, and it's only going to be this leg, which should be L cosine theta, so mgl cosine theta. All right, so our total energy of this system, E, P with respect to O, is going to be the addition of our kinetic energy plus our potential energy. And so we get 1/2 mL squared theta dot squared minus mgl cosine theta. Let's take the time derivative of this entire expression, so d dt, as observed in the inertial reference frame. And the left-hand side of this equation, the time derivative of energy, is going to be 0 because this system conserves energy. And then we're going to calculate the time derivative of each of these expressions. And when we do that, we bring our 2 down, so we get mL squared, and we'll get theta dot, and then the time derivative of this inside expression is theta double dot. So there's the time derivative of the first term. And then of our second term, we have our scalars mgl. The time derivative of cosine theta is sine theta multiplied times theta dot, and put a negative sign in front of this. And so we can start canceling some terms where we have a theta dot in each of these expressions, so we can cancel those guys. We have an m on each side, so we can cancel those if we divide through by m. If we divide through by L, then we'll get rid of one L there, we'll get rid of our only L there, and then when we solve for theta double dot, we get theta double dot is equal to negative g over L sine theta. So what's nice about this is that this was actually less work than when we derived this the first time using Newton's second law. Much less work than when we derived it the first time using Newton's second law using Cartesian coordinates. Now we're using our polar coordinates in a polar frame with adding this polar frame. But notice here that all we had to do was at the beginning say that energy is conserved. We had to prove that energy is conserved. And if we've got a system where energy is conserved, simply calculate the kinetic energy, which is 1/2 mv squared. And if you've got an expression for your velocity, that's pretty easy to do. And then the potential energy, which ends up being a really easy expression, minus mgl cosine theta. We take the time derivative of the total energy and then solve for our second order differential equation. So this is a lot less work than we're used to doing for solving equations of motion. And that's the advantage here, because we didn't have to solve for acceleration, we only needed our velocity, and we put this in terms of energy. Now, a couple things to point out is that this is really only useful as it is in very simple systems. So the requirements that we have for being able to do this are that energy must be conserved. We're not going to do this using any systems that energy isn't conserved. And in addition, it needs to be an equation, or it needs to be a system that only has 1 degree of freedom. And the reason why is because our energy isn't a vector function, right? So we've got energy here, and those are all scalars. Our potential energy is a scalar, our kinetic energy is a scalar. Certainly we use vectors to get there, but it's a scalar expression. And so a 2 degree of freedom system has to have 2 coordinates that describe its motion. And so which would mean that we would need 2 equations of motion to come out of that. And because this is a scalar expression for energy, or energy is a scalar, then we can only solve 1 degree of freedom systems to solve for the equations of motion for 1 degree of freedom systems. It doesn't have the capacity to pull those apart into multiple degrees of freedom. Now, there are ways to use the energy of a system, the kinetic energy and the potential energy of a system, to solve for more complex systems that don't have these constraints. And so those are called Lagrange's equations. We're not going to do those in Dynamics 1 or Dynamics 2 in this class. You will see those in upper division courses, such as robotics. It's a very popular method to use in robotics. Also in intermediate dynamics or applied dynamics. And simply because if you've seen or if you kind of notice the utility of using energy to solve for these equations here, it really is the same way in Lagrange's equations. If you know what to do with the energy and how to apply the particular derivatives, then you get your equations of motion very quickly. And also, you get your equations of motion in those systems without having to go through the constraint forces, which we typically have to do using Newton's second law. So let's move on and let's do one more example. This is a system that we've seen before. We did it in problem 320 in the book. And in problem 320 we derived, in part B of that, we derived the equation of motion using Newton's second law. And so this time let's derive the equation of motion using conservation of energy. Let's apply an inertial reference frame. And so here we have our reference frame I, which has an origin at point O. We have E1, that's along OC, and then E3 out of the plane of motion, and then E2, which is the cross product of E3 and E1. Our kinematics of the system are P with respect to O, R L in the E1 direction, plus X, so we have one coordinate, this is a 1 degree of freedom system, X in the E2 direction, and then our velocity, P with respect to O, observed in the inertial reference frame, is x dot in the E2 direction, because L doesn't change, L is fixed. And so first we need to establish that energy is conserved in the system. So to do that, we need to find out what forces are acting on the system that are non-conservative forces. So let's draw a free body diagram. And on this free body diagram, we have mg in the E1 direction. We have a normal force, and we can put that in the negative E1 direction. And then we have a spring force. And we've established that the conservative forces that we're looking for are gravity. Spring forces are also conservative forces. So these are conservative. And then the only non-conservative force that we have is N. And so our work on P due to non-conservative forces, R, P with respect to O, along the path P, is equal to, we'll do a path integral, in which we have N, or negative N, in the E1 direction. And we're going to dot this with ds, and this is the ET direction, so we're doing a path integral, so we need to apply a path frame. And so for our path frame, we'll just put our vectors on there, in which we have E sub t, and then En is actually undefined in this case, or not well defined, because this is straight line motion. But the most important thing to observe is that E1 is orthogonal to ET. So if we draw our vectors, we move our vectors. Out here we get that E1, this is also En, and then here's ET as well as E2. So just showing us that En is orthogonal with ET, and if that's the case, then the work due to non-conservative forces is equal to 0. And, you know, like, as always, the work due to constraint forces is equal to 0. So let's find our expression for our total energy. E, P with respect to O, is equal to T, P with respect to O, plus our potential energy, P with respect to O. And so kinetic energy, T, P with respect to O, is equal to 1/2 mass times V, our velocity P with respect to O observed in the inertial reference frame. The norm of this squared is equal to 1/2 mx dot squared. And now our potential energy is actually due to two different forces. We have a conservative force of gravity, and we have our conservative force due to our spring. So our potential energy, we'll break this up into two parts, in which U, P with respect to O, is going to be UP with respect to O of mg, our gravity, plus our potential energy, P with respect to O, of our spring force, Fs. So let's take care of our potential energy due to gravity first, and that's equal to mgy. We have the same constraint on y, in which y has to be the distance above point O, and so this will be mg, and then r, P with respect to O, and to get that distance above, that's in the negative E1 direction, so the distance above the negative E1 direction, and so we're going to dot this with negative E1, and our expression here is negative mg. We'll put in our position vector. Our position vector is L in the E1 direction plus x in the E2 direction, and that's dotted with E1 because we moved our negative sign out. And so we see here this is equal to E1 dotted with E1, so we get negative mgl, and then we have an E2 dotted with E1, which gives us 0. We're moving on to our potential energy, P with respect to O, of our spring force, and we see that from the book that that's 1/2 k, and then this is x squared, and this is where x is the change in length of the spring. So it's the change in length of the spring, and this is with respect to the resting length. And so if we look at our system here, if we get our full length, which is x and L are the two legs, then the hypotenuse is going to be our full length. Our resting length, stated in the problem, is that the resting length is L. And so when we draw this triangle where L is constant, x is changing, it's a function of time, our hypotenuse is L squared plus x squared, and so our expression for our potential energy of the spring is 1/2 k, and then the change in length with respect to the resting length is the square root of L squared plus x squared minus L, and it's that entire quantity squared. So we just square that entire piece, and that's our potential energy of the spring. So now we insert these into our expression for our total energy, in which we get that our energy, P with respect to O, is equal to 1/2 m x dot squared minus mgl plus 1/2 k times the square root of L squared plus x squared minus L squared. Right, we take the time derivative of this entire expression as observed in the inertial reference frame, and so the time derivative of our energy is equal to 0 because energy is conserved, and then we're going to take the time derivative of each of these pieces of this expression. So for our first piece, 1/2 m x dot squared, the time derivative, because we're going to pull our 2 down, and so the time derivative ends up being m x dot x double dot, and then the time derivative of our potential energy is 0 because it's constant, so that's minus 0. And let's go back to this. So our potential energy, it should make sense that it's constant because the mass is only sliding along this bar. It's not changing height at all. If it changes height, then there's going to be a change in potential energy based on the state. But in this case, regardless of the position, regardless of the velocity, regardless of the acceleration, it's going to be the same. And so our time derivative is equal to 0. And then, for this last expression, we bring down our 2. So then we only have a k for our constant. So that's plus k. And then we just bring down what's inside the parentheses. So that's square root of L squared plus x squared minus L. And then we take the time derivative of what's within the parentheses. And so the time derivative of this first part, the square root of L squared minus L squared plus x squared, this is L squared plus x squared raised to the negative, or raised to the 1/2. And so we bring our 1/2 down. So it's 1/2. And then we put that expression there. We're going to drop the power there from 1/2 to negative 1/2. So L squared plus x squared, and this is to the negative 1/2. And then our next part of this expression is the time derivative of L, which is 0. And then we take the time derivative of what's within this parentheses. And so L squared, the time derivative of that is 0. And then the time derivative of x squared is 2x x dot. And so here's our expression now for the time derivative of our total energy. Let's simplify that expression. So we get 0 is equal to, just move this down, m x dot x double dot. Okay, potential energy was 0, the time derivative of that. And then let's simplify this part, so it's going to be k. And let's move this expression into the parentheses. And so this is L squared plus x squared to the negative 1/2. So when we put that underneath our first term, that gives us 1. And then so this will be minus L divided by the square root of x squared plus L squared. And then our 2 cancels with our 2 in the denominator. And then we get x times x dot. So continue to simplify this and solve for x double dot to get our second order equation of motion. We can divide this entire expression by x dot, which gets rid of those terms. And then when we solve for x double dot, we get x double dot is equal to negative k over m multiplied times 1 minus L divided by the square root of x squared plus L squared. And that entire quantity is multiplied by x. And this matches what our equation of motion is that we solved in problem 320, and we solved that before using F equals ma. And so once again, the advantages here of doing this are that when we have a 1 degree of freedom system that conserves its energy, that we really don't have to do too much work here, in that we find our kinematics only through our velocity. And so this is as far as we need to go. We don't need to calculate our acceleration. And then we find our total energy. We take the time derivative of the total energy. So in this case, our total energy was composed of our kinetic energy, and then we had 2 expressions for our potential energy, one due to gravity, one due to a spring. And it gives us a scalar function. Take the time derivative, and then solve for our second order differential equation. Alright, that does it for this lesson, and I'll see you in class.